Welcome to Introduction to Rocketry Airframe Track.
Hello, so this presentation is going to cover a whole bunch of general information about rocketry. We think it's important to go over all this stuff right at the beginning because otherwise you might have a hard time figuring out what we're talking about later on. And because everything in a rocket sort of affects everything else, there's no independent systems. Um, so that's why we're doing this all at once right at the beginning. We don't expect you to remember all the details, but you can look back at this presentation if you're like if you're confused about something in the future, and you can look at the documentation that's linked on the previous slide um, for more details about the stuff we cover in this presentation. So the main point of amateur rocketry is to learn applied science and engineering by applying science and engineering. And along the way, you'll get to know a great community of fellow enthusiasts and learners, and you'll have a lot of fun.
So what's the point of Aerospace NU? Aerospace NU is basically a place for students to go if they're interested in aerospace development. It's that simple. We exist to pull together the resources, be that knowledge or university funding or insurance risks, that kind of thing, all in one place so that we can do really cool projects like you can see in this picture here. Aerospace NU basically acts as an administrative body to get permission to do cool rocket launches with the university. We exist so that we can handle things like insurance, transportation, risk services, and make sure that you guys can basically research and work on anything that you want. So yeah, that's why we exist as an organization.
All right, so what is the point of intro? The point of intro to Airframe is to learn and build a community. So we're all here to learn the basics of rocketry, how to design and build a kit rocket, and apply the skills that we learn throughout the fall to design a larger rocket and run simulations and perhaps build that rocket in the spring. And building a community is very important. You know, rocketry is a very fun hobby, and it's great to share that with other engineering or science majors or any majors and just share experience and have fun. All right, so here's the distribution of people. We have 20 students in Intro to Airframe and 6 mentors. So we split everyone up into 5 groups of 4 people, and in each group there will be a dedicated mentor, and we'll have one mentor left over that will float between each group and periodically check in and see if anyone needs help. Um, and each group will have a Discord channel, so if you have any questions at any point, feel free to post that in the Discord channel, and your mentor will get back to you pretty quickly. And you can rename the channel and come up with a group name if you want.
So now we're going to look at some basic rocket physics. A rocket, while it's being powered by its engine, can be described by Newton's second and third laws. And basically, the gist of it is that a rocket, you can think of it as a body that's spewing hot gases out the back of it at a high velocity. And those gases have a um, velocity relative to the rocket in the opposite direction of the rocket's direction of motion. Um, and those gases also have mass, so they've got this mass and this velocity, so they have momentum, and that momentum is in the um, opposite direction to the direction the rocket's going. Um, so for momentum to be conserved, the rocket itself also has to gain momentum in the direction it's going for momentum to be conserved, because you've got the exhaust gaining momentum in the backwards direction, so therefore the rocket must gain momentum in the forwards direction for the net momentum of the system to stay constant. The system being the rocket and the exhaust. So then you can do some calculus on that concept and get this equation here. And if you want more information about the details of that derivation, you can take a look at the documentation we wrote up. That's linked in the notes for this slide, and that'll go into more details of how you get there and also how you account for acceleration due to gravity and stuff like that. Then also, I mean, you don't really need to know the details of all this stuff for what we're doing in this class, but it's pretty cool stuff. So if you're interested, definitely take a look. So now we're going to look at the other, or one of the other main components of rocket physics. That's the aerodynamics of the airframe itself, so the outside of the rocket, how that travels through the air. So there are a couple terms that are important to understand. The center of pressure of the rocket is the point at which the net radial pressure force acts on the rocket. And in this diagram, the center of pressure is represented by the red dot down towards the fins, and the center of pressure is determined largely by how big the fins are relative to the rest of the rocket, because as you can imagine, if you make the fins bigger, then if the rocket is traveling in a non-axial direction, that is, it's not traveling along the line from its tail to the tip of its nose cone. If it's traveling in a non-axial direction, then you're going to end up with air pushing on the side of the rocket, exerting this radial pressure force, and that force will be focused down towards the tail where the fins are, if the fins are really big, because they're going to catch the air, essentially. Then the center of mass is the average position of the mass of the rocket. So if the rocket's going to pivot in midair because of pressure forces acting on it, radial pressure forces, it's going to pivot about that center of mass. So you could sort of think of the center of mass as a bit of a fulcrum. And the farther apart the center of mass is from the center of pressure, the greater the moment, or maybe you prefer to think of it as torque. It's essentially the same thing. But the greater the moment or the torque about that center of mass. So if you because you essentially have a longer lever arm about that fulcrum that is the center of mass. So you can see in this diagram, the lever arm length is Cp minus Cg, Cp being the distance from the tip of the nose cone to the center of pressure, and Cg being the distance from the tip of the nose cone to the center of mass. Cg, center of gravity, center of mass, center of gravity, it's all the same thing in this context anyway. This is just a little bit more about the effects of this phenomenon. So if the center of pressure is situated behind the center of mass in the rocket, or in this diagram, that's below, so closer to the tail where the fins are, then the rocket will be self-stabilizing essentially, because as you can see in the picture on the left, if the rocket's sort of tilted, but it's, say, going straight up, meaning that it's traveling in a non-axial direction, the air is going to push down on the left side of the bottom of the rocket, and it's going to cause it to swing back around, cause the fins and the tail to swing round to the right. So then now it's traveling in the axial direction, and there's no longer a pressure force, a radial pressure force that is on the center of pressure down there. And that keeps the rocket stable. So if it starts to skew, then the center of pressure the force on the center of pressure will cause it to swing back around. And that stability is measured with what's called the cal. That's short for caliber or stability caliber. And the cal is the center of pressure minus the center of gravity divided by the diameter of the rocket. And as I mentioned before, center of pressure is the distance from the tip of the nose cone to the center of pressure. Center of gravity is distance from tip of the nose cone to the center of gravity. And then diameter, that's obvious. So you generally want the cal to be around 2 because that provides a good amount of stability without going overboard, and I'll explain what going overboard is in a second. Too far below 2 will mean that the rocket won't correct for non-axial movement well enough, so it'll be unstable and might start tumbling. And you can also think about what would happen if the center of pressure were above the center of mass in the rocket. That would cause the rocket to flip around and start traveling with the tail first. Only it wouldn't stay like that for long because the motor's down there spewing hot gases. So things would become pretty chaotic pretty fast. So that would be bad. So can't have the cal too low, and definitely don't want it negative. Cal too high, though, will cause it to overcorrect. So essentially, if there's any non-axial movement, it'll cause the tail to swing back over too far, and then there'll be a pressure force on it on the tail from the other side. It'll cause it to swing back the other way. It'll keep doing that and oscillating. So that's not stable. That's not good. So you don't want to go too far above 2 on your cal either. Yeah, you end up with lots of weather cocking then too. So when the rocket is first launched, when it takes off the launch rail, that's the structure that sort of helps it get going in the right direction, right? When the motor is ignited. Once it gets off that launch rail, it's still going relatively slow. So any wind has a disproportionate effect on it. So if you've got wind coming in from the side, now all of a sudden its relative velocity with respect to the air is no longer axial, and it causes it to pivot into the wind. And if your center of pressure is too far below your center of mass, it'll pivot into the wind a ton. And now all of a sudden your rocket's going sideways instead of up, which is not what you want. So yet another reason to not have your cal be too high.
All right, so we've talked a lot about the physics behind rocketry and what makes them actually fly. Now I'm going to talk about what the actual parts of a rocket are, because that nomenclature is going to be really important going forward, so we're all on the same page and know what we're talking about, right? So we've got a lovely little diagram here with most of the parts labeled. Starting from the front, you've got the nose cone. That's the cone on the front of the rocket, and that is primarily for aerodynamic purposes, right? So when you're flying into the air, it allows the air to slip around the rocket more easily than if it were just, say, a flat-ended cylinder. The main body of the rocket is called body tube. That's the skin that goes around everything on the inside, sort of the main structure. So that's body tube. And then if you have more than one piece of body tube, they're held together with something called a coupler, and that's really just a slightly smaller diameter tube that fits inside the body tube and allows you to sort of make a joint between them that can't bend around. Next up is rail buttons. They're also called launch lugs. So rail buttons are a way to launch your rocket, right? You need a way to stand it upright before it's lit, so that when you light the motor, it will go straight up and not like sideways or something like that, which would be bad. And so the way we do that is we have a little button on the side of the rocket, and that slides into just a vertical rail. And then when you light the motor, it just shoots it off the rail and it keeps going straight up. So that's what a launch lug is. Fins, Andy talked a lot about why fins are super important for stability, and those are usually at the back of the rocket because you want to move the center of pressure towards the back end of the rocket. And then the motor retainer is a piece that holds the motor in. That's super important because you don't want your motor falling out, then the rocket won't fly, then you've got a stick of explosives not in a rocket. All bad things. Motor retainer is important for that. So that's all the sort of components on the outside. Moving inside, one of the most important things that goes in a rocket is the recovery system. So you need parachutes, you need a recovery system so that your rocket doesn't just nosedive into the ground. That's dangerous and also will destroy your rocket. Two bad things. So the parts of a recovery system are parachute, shock cord, and Nomex. So parachute is the thing that actually slows down the rocket's descent. I'm sure you've all seen a parachute before. So you know what that is. Shock cord is just what we call the rope that attaches the parachute to the rocket. That's really all it is. And the Nomex blanket is a piece of fireproof cloth that gets wrapped around the parachute, and that protects it from getting burned or like a little bit melted because the parachutes are made of plastic. It basically just protects the parachute while it's in the rocket, make sure it gets out safely and can function as necessary. So other things that can go inside a rocket, you can put a payload in there, and payloads can be anything from cameras to science experiments to little stuffed animals. Really anything that you just put in a rocket that's not part of the rocket itself is called a payload. So electronics are important for controlling flight events. A lot of times on bigger rockets, you need to tell the parachutes when to deploy. And so we use electronics for that. We use electronics to collect sensor data and all sorts of stuff. Brian's going to be talking about that more in a little bit. Bulkheads are just discs that go inside the body tube and they separate different sections of the rocket. So for example, we'll put a bulkhead between the motor and the parachute to prevent just so they're separate sections, right? So that's what bulkheads are. And then there's a couple of pieces that go into holding the motor in the rocket. The first one is a centering ring, and that's basically very similar to a bulkhead. It just has a hole in the middle, so it's a ring. And the way that works is the motor is a slightly smaller tube than the body tube. So you slide the motor into the center hole of the centering ring, and then you slide the centering ring and motor into the body tube of the rocket, and that holds the motor in the center of the tube. The motor tube is that slightly smaller tube that I just mentioned. It goes around the motor. And then the motor itself is solid propellant. So that most of the motors that we use are ammonium perchlorate fuel. And that's just solid propellant motors. And Thomas is going to be talking a little bit more about those in a bit as well. Alright, so I talked about what the parts of a rocket are, and now we're going to go over what the parts of rocket flight are, because that's also some terminology that's going to come up a lot. So you can see this lovely diagram over on the side that's got sort of the arc of a whole rocket flight. So there's a couple different stages when you're launching a rocket. The first one is called boost, and that's just the time when the motor is burning, so the rocket's being actively propelled upwards. After the motor burns out, it starts coasting and it continues upward. It's got momentum carrying it up still. And so it coasts until the combined effects of gravity and drag slow it down and it stops going up. The point where it stops going up, arcs over, that's called apogee. That's the highest altitude that the rocket will reach. And then all the way back down to the ground is called descent. So there's a couple of parachute events in rocket flight as well. For bigger rockets, we put out a drogue parachute at apogee. That's just a smaller parachute that slows you down a little bit. And then you have a main parachute deploy at a lower altitude. So in this diagram here, you have a drogue come out at apogee, and then you have your main parachute come out at 550 feet. In this diagram, there are two main parachutes. It can be one parachute. That's just the way this one is in particular. This particular flight also had a payload deployment, and so there are flight events and parachutes associated with that if you're doing that. But for a basic rocket flight, it's drogue and main parachutes. All right, so I keep talking about recovery and parachutes and how important they are. And now we're going to get into a little bit more about that, because it really is a tremendously important part of rocket flight. So first up, how does the parachute get out of the tube? Right? You've got your rocket, you've got a parachute in a section called the parachute bay, but how does it get out? So the way we do this usually is you have a little black powder charge. Black powder is just gunpowder. So you have a little bit of black powder in like a little cylinder charge inside your rocket. And then you light that, and that combustion reaction pressurizes the inside of your tube, and that forces the tube apart, and also blasts the chutes out. So that's how you get your parachutes out. We also, to fill up space in the charge, sometimes you don't want as much black powder as there is space in the charge you're filling, so any extra space gets filled up with something called dog barf. I don't know why it's called that. It's literally just bits of shredded up newspaper. But that provides more fuel for the combustion reaction and makes sure that you're getting the pressure you need. We light the charges with electric matches or e-matches, and that's where the electronics come in, is that they can send a signal to light the e-match, and that will actually light the charge and get the parachutes out. So that's how parachutes get out. I mentioned on the previous slide that bigger rockets use two parachutes, a drogue and a main. So the reason we do that is that when you're going very high, if you deploy a big parachute at apogee, you can drift really far if there's wind, and that just is inconvenient for recovery. You can drift out of the open space you're in. We've had, if it's near a lake, it will drift over the lake. It can drift over trees and get stuck in a tree. Both of those things have happened to us. So to avoid that, you deploy a small parachute at apogee, and that slows it down a little bit so it's not just falling ballistically. And then you deploy your main parachute a lot lower, so it will reach the ground at a safe speed, but it's not drifting really far on the way down. The reason you have a drogue come out at apogee and not just a main parachute come out lower is that if you fall ballistically means no parachute. If you fall ballistically from apogee to your main deployment altitude, by the time you reach your main deployment, the rocket will be going very, very fast. And so when you go from very fast to suddenly very slow because your big main parachute has come out, that creates a lot of shock load, and that can break your shock cord, which is bad for the rocket. It can break your rocket. So you have the drogue to slow it down a little bit, and then you have the main to slow it down to a safe landing speed. And that's called dual deployment because you have two parachutes. For smaller rockets that aren't going as high, where you don't need to worry about it drifting really far, you can just put one larger parachute in, and that's called single deployment. So I mentioned the Nomex blanket on the first slide when I was talking about parts of a rocket. But that's pictured in the lower right corner there. That's that green square. And so yeah, the Nomex is to protect the parachute from the black powder charge, mostly. Yeah, I guess other pictures. The top left picture there is the Orion capsule coming down under its main parachutes. Because parachutes are used all over the place, and I think that's really cool that we're using some of the same stuff that NASA uses for their stuff. And then the middle picture there is a rocket coming down under its main parachute. That's the big black and orange one. And you can also see the drogue that they used. That's the little red and white one there. Is now just on the line as it's coming down under main. So yeah, recovery is important because if it doesn't have a parachute, it will come down ballistically. Then your rocket's a missile. That's bad. That's a safety concern, and it will also break your rocket. And we don't want either of those things to happen. We want to be safe and we want to have fun.
Alright, so we've talked about the flight profile and how you want to deploy your drogue at apogee and how you want to deploy your main parachute at about 400 500 feet, and we've talked about the ways in which you deploy your parachutes, but you might be wondering, how do we even detect where we are in our flight path? And so we use electronics. We use a mix of commercial and custom electronics that measure everything from acceleration to your orientation with gyroscopes to the pressure. And pressure is typically how we get altitude readings. And we use acceleration to figure out if we're at apogee. And we can also record data, we can deploy payloads, we can even have radio to communicate with a ground station and get live data in order to track the rocket, so on and so forth. You can get really creative. So on the right side of the screen is what a typical eBay looks like. I say typical with a strong emphasis on you don't need to follow this. We want you to break the rules here and try and optimize and make it better. We've already, in the last 4 years that I've been at Northeastern, gone through a lot of different design ideas and iterations, and this is quote-unquote typical in that it's a sled or a piece of wood that has been laser cut and 3D printed, and 3D printed housings and electronics are then bolted down onto it. And you can actually see holes cut out into the body tube that are access ports for the switches. So yeah, the electronics are on these sleds, and the sleds and the bulkheads that sandwich them are together known as the electronics bay. And we'll get more into all of this nitty-gritty electronic stuff when we are going to plan for the spring.
Okay, so now we're going to talk a little bit about airframe sizing. 38 millimeter, 54 millimeter, and 75 millimeter are common tube sizes that amateur rocketry manufacturers make, and they're pretty small and light, and they don't cost very much to build rockets those sizes. But they're generally a little bit too small for what we like to do in this club. So we often opt for 4-inch tubes or 6-inch tubes. But even 4 inches can be a bit crowded, as you can see from that eBay there on the right. There's a lot jammed in there. So we often go for 6 inches, like that rocket on the left. And we even go bigger than that sometimes. Redshifts currently looking at 8-inch tubes for the liquid fueled rocket. But that's airframe sizing is an important decision you need to make early on in the design process, because that dictates what else you can jam in the rocket, what your payloads need to look like, stuff like that. One thing I'd point out on this slide too is on the 6-inch rocket there on the left, it's got a transparent section made out of acrylic, so it's see-through, so you can put cameras in there, and you can also put antennae in there for radio communications. And that can be important on rockets where the tubing is carbon fiber, because that'll block the radio signal.
So now for a review of solid propellant rocket motors. In Intro to Airframe, we'll only be using solid propellant motors. The other main type of rocket engines are liquid-based, which is the kind of liquid rocket engine group in AeroNU has experience with. But for solid propellant motors, different motor diameters and cranes have different characteristics. The motors we use have different diameter values given in millimeters, so like 18 millimeters, 29, 54, and so on. Higher impulse motors have larger diameter motors, essentially. And within motor casings are propellant grains. A grain is an individual stack of propellant, about 2 inches long, and several of these grains are stacked in series within the motor casing. So more powerful motors have both larger diameter and more of these individual propellant grains. A little bit about ratings. From the letter A to the letter O, there's a designation for the impulse range of a rocket motor. For instance, the letter rating listed, K1440, the K designates an impulse range from 1,280 newton seconds to 2,560 newton seconds. Impulse you can think of as the average thrust of the motor multiplied by the motor burn time. And as you keep advancing in the alphabet, L, M, N, the impulse range doubles for each letter. So a letter difference might not seem like a significant change, but there's a clear difference in flight performance you'll find. From 1.25 newton seconds for the lower bound of an A motor up to 40,960 newton seconds for the upper bound of an O motor. And the number listed, the 1440, designates the average motor thrust in newtons. So 1440 newtons is the average thrust for this specific motor. Looking at thrust curves, two motors with the same impulse rating can have wildly different thrust curves, and this is due to the actual propellant grain shape and the number of grains in a motor. You could have a slow burning motor or a very fast burning motor that accelerates your rocket right off the launch pad. Certifications are required to launch rockets with higher power motors. The high power designation for a motor starts at an impulse rating of H. And outside the bounds of intro, club members occasionally pursue certifications with an organization called the National Association of Rocketry, or NAR for short. And by achieving these certifications, someone can launch higher impulse motors. So the certification process entails building a rocket from scratch, launching with a high power motor, and also recovering that rocket. There are different requirements for each level of certification, like a multiple choice test for L2 or a full rocket design report for L3. But going that path is a great way to gain design and manufacturing experience while also advancing within the club. And motors are delicate and need to be treated nicely, which is something we'll talk about on the next slide. So regarding rocket motor safety, keep your motors in a cool, dry location away from sources of heat. The rocket motor igniter that actually sets off these motors is a high current electric match, which we'll learn more about later, but we don't want any motors going off before the launch date. For each individual rocket motor, you can find the MSDS, or Material Safety Data Sheet, online for more information, like what is the actual recommended storage temperature range, or the NFPA, National Fire Protection Association rating. And I took a screenshot of the NFPA rating for the motor you'll be using for the kit rocket. And if you haven't seen this symbol before, you're bound to see it a couple times as an engineer or scientist. So I'll just give a brief summary. The blue diamond is the health hazard, the red diamond is the fire hazard, and the yellow diamond is the reactivity hazard. The number associated with each section indicates the risk, with a higher number corresponding to a higher level of danger. So for a rocket motor, you can see 3 for fire hazard and 1 for health and reactivity hazards. And something to note is the white diamond at the bottom includes additional information like whether the material is radioactive, or as you can see in the case for rocket motors, there's an indicator for oxidizer by the letters OX.
So before we go about actually constructing our rockets, we spend a lot of time in design and simulation. We'll be focusing on that quite a bit throughout this course actually, and the two main softwares that we're going to be using are OpenRocket and SolidWorks. Open rockets are really easy to free download that you can find pictured in the top right up here. It's good for finding flight profiles and basically how your rocket will perform based on weight, based on aerodynamics, and what kind of model motor you have in the rocket. So it's really good for preliminary calculations. SolidWorks, on the other hand, allows you to actually create, it's a CAD software, so it's a 3D modeling in its completeness. SolidWorks is available with a student license, and we'll get you guys through that, and we'll actually start working in SolidWorks in our second meeting. You'll actually start using SolidWorks in the second half of your Cornerstone of Engineering class. So you actually have a leg up on other people here too, after we teach you a little bit about it. There's alternative softwares that people in the club have used in the past. I know RasAero and RocketSim are basically substitutes for OpenRocket. We've moved more towards OpenRocket in the past, but those two are totally available for your use as well. I believe they're also open source. ANSYS is a much more in-depth software, which is typically used for our fluid sims. So for the engine itself, the liquid bipropellant engine that's being used in Redshift is using a lot of ANSYS sims in order to figure out what the heat transfer is like, how the fluids flow through the actual engine itself. So it's really good for in-depth, highly technical calculations, but we won't be using that a whole lot in this course. And basically the whole point of this is that we can integrate well with the other parts of the rocket. So what you guys are learning here is how to create an airframe that fits the needs of our situation, and by being able to create a CAD model beforehand, it helps us communicate with the other tracks to make sure that things fit together nicely. So that's our goal here. Everything will fit together once we're done, and we can have a working model as we go through our designs. After we finalize our models in our design and simulation phase, we move into manufacturing. So we don't buy all of our parts off the shelf. We actually have to make quite a few things custom, especially in the more technical projects like Redshift. They'll be doing a lot of machining to create their parts. There's a couple techniques that we have available to us. We typically have access to the lab in Forsyth. However, as of this year, we have not yet been given permission to work in there, so that cuts down our capacity a little bit. But I'll be just describing some of the things that are available to us in the Capstone lab and our typical Forsyth lab, should that become available in the future. The first technique that we have is 3D printing. We have 3 Prusa 3D printers available to us, which is really great for prototyping. If you haven't done any work with 3D printing, it basically allows you to create any custom piece you'd like in really rapid time. So it's typically out of plastic polymer. We do have some carbon composite polymers that we can use as well. So it's great for prototyping, and it's great for niche case uses, and especially for things that are difficult to machine. So this is something we might end up incorporating into your guys' rockets in the second half of this course. And 3D printing is just overall a heavy use manufacturing technique for us for sure. Milling is another thing that we have in the Capstone lab. Mills are essentially a drill press that can slide and cut through metal. So the milling allows us to create custom metallic parts, be that aluminum or stainless steel or any other composite steels that we have available to us. After you've created a model in SolidWorks, you're actually able to use a software called CAM, which allows you to basically teach the mill what you want it to do. So it's a really cool technique. It's an art really, so it takes a lot of time. We won't be going into that just yet, but in the second half of our course, we will probably be getting into this a little bit. We also have a water jet cutter, which is basically like a really powerful stream of water that cuts straight through steel and traces an outline. So it's good for 2D shapes that we have to cut out. So for a lot of our bulkheads, we might use water jet cutters. We also have a laser cutter, which is basically the same thing but for wood instead of metal. So yeah, we're very flexible in terms of what we can actually create. But the biggest thing that's really important is that you need to be wearing appropriate PPE before you're using any of these equipment. So let's say you're cutting through fiberglass or carbon fiber tubing. You're going to want to make sure you're wearing a respirator, because that stuff sucks if you breathe it in. It'll cause lung damage, and you should be wearing gloves and glasses too, because of the debris that comes off of it as you're cutting it can be pretty dangerous. So the idea here is basically, before you go ahead and use something, ask somebody who has experience with it, make sure that you're using appropriate PPE. So we're not able to manufacture all of our parts, motors especially, the solid fuel motors that we use. When we can't manufacture things ourselves, we go to these various vendors to gather the things that we need. For motors, we typically go to Chris's Rocketry Supplies and Animal Motor Works. They're very reliable so far. They've got a huge assortment of rocket motors for different apogees and different impulses. So if you want to check out what's available, check out either of those sites. They're hyperlinked in the meeting notes, and they're hyperlinked in the documentation if you'd like to just get a quick link there. For things outside of the motors, we have a lot of airframe parts that we need. So Apogee is a fantastic site. They're basically like the Amazon for rocketry supplies. So if you want to buy a 3-to-1 ogive nose cone, you can go to Apogee. If you want to buy like a bulkhead that's this size, if you want to buy coupler, you want to buy tubing, Apogee's got you covered. So they're a good place to go to. Mad Cow is basically, it's similar to Apogee in terms of what they actually have available to them. And finally, McMaster-Carr. McMaster-Carr is basically your go-to for engineering when it comes to hardware. They sell literally anything you can think of. They sell like entire cubicles. They sell bikes. They sell specific screws that you need. They sell like anything you can think of. So McMaster-Carr is a great place. We go to them quite frequently. And their shipping is really, really fast. So that's also going to be your go-to when it comes to actually purchasing parts.
So you've built a rocket, and obviously you want to launch it. So what do you have to do? First, you have to ask yourself, is this a club rocket that I'm launching with the club? If so, you need to submit some paperwork for our insurance. Obviously, you want to then go through and check that your ejection charges and your electronics works. And you want to prepare a launch kit, which has basically spares of everything and anything you could possibly need. And you want to make yourself some checklists to go through before you launch. Then on the day of the launch, once you arrive, you'll want to pack your charges, your parachutes, and your Nomex blanket. You'll go to the range safety officer, and they will give you a flight card. They'll weigh your rocket, and they'll inspect your rocket. And then they will tell you that you're good to go or not, and you can go up to the pad. So once you're on the pad, first things first, you load your rocket onto the launch rail. You want to take the 2 wires that lead to the control box that the range safety officer uses to start your engine, and just take the 2 leads and tap them together just to make sure there's no static electricity. You don't want to hook those up to your igniter when it's in the engine and start it while you're there. So then I guess I should also say, before the pad you want to load your motor. I figure that's a little obvious, but you don't want to be doing that at the pad. But you don't load your motor igniter until your rocket is on the rail. So you stuff the motor igniter as far back into the motor as you can, and you connect it to the launch controller wire leads. At this point, you want to take a picture. I mean, who doesn't? And if you have an electronics bay, this is when you would activate your deployment electronics. You want to do it at the very end, just because if there is any malfunction, or if you have to adjust your rocket, you don't want to have to take your rocket off the rail with your electronics on, because it might detect the change in orientation as reaching apogee and then set off the charges while you're taking it off. So no bueno. So once everything is all set, you want to activate your deployment electronics. Make sure that they are properly activated. If they're, for example, stratologgers, and they'll beep at you. Then you just head back, get ready to take some video, and cross your fingers.
There are many failure points in rocketry, so here we'll discuss some of the most common ones. One of the primary recovery failures is zippering, which occurs when the rocket is moving at a high speed and a separation event occurs. The deployed parachute slows the rocket down, but it does so within a short time frame, making the shock cord that connects the parachute to the rocket, which is normally Kevlar or nylon rope, cut into the body tube. In the best case, the body tube sustains some damage, and otherwise the recovery is successful. You can see on the right someone applied a line of epoxy to fill the zip ring mark on their body tube after recovering it. But in the worst case, the shock cord is cut and part of the rocket falls without a parachute. Ideally, zippering would not happen if the deployment events are timed perfectly. Another recovery failure is separation or electronic failure. Separation failure occurs when the rocket sections fail to separate during a deployment event. This could be due to insufficient black powder, high friction forces between coupler and body tubes, or an electronics failure. Depending on the complexity of the rocket and which deployment event is affected, a separation failure could result in a ballistic entry where the rocket returns to Earth at a high velocity and buries itself underground, or the rocket lands with partial parachute drag force, which also results in damage. To combat this type of failure, it's good practice to include backup electronics and backup black powder charges in the event that one system fails to separate the rocket. The last failure point we'll talk about is instability. The instability of a rocket is determined by the relative positions of its CP, center of pressure, and its CG, center of gravity. If the positions are too close together, something will happen known as low cal or low caliber, which can easily result in an unexpected flight profile and decrease the chances of a successful recovery. On the other hand, if the rocket's cal is too high, weathercocking can ruin the rocket's recovery. This is where the lateral wind forces cause the rocket to fly into the direction of the wind, sending it away from the launch pad. One might think this is fine since once the parachutes deploy, the rocket will drift back to the launch pad via the wind force. However, the launch site is only so large, and if line of sight with the rocket is broken, the chances of recovery become slim, assuming there's no tracking capability on the rocket. A related issue is a rocket that is low velocity when it leaves the launch rail, which results in a tilted flight profile. The rocket should be moving quick enough when it leaves the launch rail to minimize this type of failure. If you're interested in learning even more about rocketry, there are some resources available that we wanted to tell you about. In terms of documentation, for each intro presentation, there's a Google Doc that goes further in depth on each topic that you will have access to. So if you're a visual learner and the concept we're describing during the presentation doesn't make total sense, check the documentation for supporting facts and figures. Apogee Components is a model rocketry components vendor that has some great learning resources in the form of instructional videos by Tim Van Milligan, the founder of Apogee, technical articles describing rocket physics and building techniques, as well as a ton of rocketry components available for purchase or research. NAR, or the National Association of Rocketry, has more learning resources like instructional videos and information on the high-power rocketry certification process. There's also a pool of questions online that help you study for the L2 written exam. That is also a good resource if people want to specifically learn more about high-power rocketry. Here are the installation links for OpenRocket and SolidWorks. And OpenRocket is a free software, so you should have no trouble downloading that and using it. SolidWorks is fine if you want to download it onto your personal PC. However, if you have a Mac, you'll need to either access SolidWorks through VLab or VMware Fusion, or have a workaround like Parallels or Boot Camp. So if you have a Mac, you will have to go through a little more of a process in order to access SolidWorks, but you should be fine. Alright, so that's the end of this presentation. If you have any questions, feel free to direct them to your mentor in Discord. And we've fed you a lot of information in this presentation, so don't worry if everything doesn't make total sense at this point. It will in time.